Welcome to Analytical Chemistry classes. Here, we will see the third and last part of the solvent extraction or liquid-liquid extraction. If not seen part 1 or part 2, please see to understand. In this part we will learn about the different modes or mechanism for separation of target substance, solute, molecule, chemical species from one phase to another phase. Let us start another interesting and highly useful topic on solvent extraction, that is different modes or mechanism for solvent extraction as we seen in the previous part 1 and part 2. Modes of extraction is like hunting a fish from sea, pond or river. Based on the size of fish present in water system we change the fishing net having different pattern, and finally take out the fish from big water system. Similarly, the different chemical species from aqueous water system is taken out using different modes of separation. Here, we will 5 more important modes or mechanism for solvent extraction or separation of chemical species from aqueous solution to organic solvent. First one is chelate extraction, and second one is ion pair extraction, third one is extraction by solvation, fourth is synergic extraction and fifth one is crown ether extraction. Let us see, the first modes or mechanism for separation of chemical species from one phase to another phase is chelate extraction. The word chelate comes from the Greek word chelate, meaning claw, like a crab's claw. This term was introduced by chemists to describe how the ligand grasps the metal ion with multiple bonds, just as a crab uses its claws to grip something. In the instance, EDTA, ethylene diamine-tetraacetic acid, is a hexadentate ligand that binds to metal ions such as K or Phe through 6 donor atoms, forming a stable chelate complex. The image of crab symbolically illustrates chelate extraction, where a metal ion, Me, is held tightly like a crab's claws by a chelating ligand through multiple coordination sites such as oxygen or nitrogen atoms. This forms a stable ring-like complex, making the metal more soluble in the organic solvent. Such chelation enhances extraction efficiency and selectivity by forming neutral, lipophilic metal ligand complexes. Generally, the chelating ligands play an important role in extraction of metals. Metal chelates represent the type of coordination compound in which a metal ion combines with a polyfunctional base capable of occupying 2 or more positions in the coordination sphere of the metal ion to form a cyclic compound. The group of the base must be so situated in the molecule that it permits the formation of a stable ring. The below image shows the general formula for the formation of metal complex with chelating agents, where X, Y is chelate, B is donor atom such as O, S, N or X is halide ion, and M is metal ion. See here the examples of chelate extraction for separation of nickel, chromium, lead, copper ions from sample solution of soil, food, vegetable, etc. A. In the image shows the formation of nickel with dimethyl glyoxime, DMG, which is organic reagent, forms pink-colored complex with nickel present in sample solution. Similarly, the B. image shows the formation of chromium with diphenyl carbazide, DPC, and C. in image shows the formation of complex with lead ion with dithiazone, and finally, the D. in the image, complex of copper with neocuproene, and these complexes can be extracted using organic solvents such chloroform, hexane, petroleum ether from aqueous solution. Second modes of separation or mechanism by which chemical species can be extracted is ion pair extraction, which involves formation of a neutral complex between oppositely charged ions, allowing transfer of ionic species from aqueous to organic phase, enhancing separation and extraction efficiency. In such a system the best separation are possible with a good diluent. The structure and branching of the amine, and the nature of the diluent affect the process of extraction. It has been found that the tertiary amines, R3N organic, given below in the chemical reaction, is found to be the best extractants for the extraction of anionic complexes of metals as shown as AB- in the reactions, along with mineral acids that is H+ ions, while the primary and secondary amines are good for the extraction of anionic complexes with organic carboxylic acid. Next we will see the example of ion pair extraction for separation of a ferric ion, by forming negatively charged chlorocomplex such as FeCl4- which is extracted by positively charged tertiary amine, that is R3NCl- organic shown in the chemical reaction, to form a neutral ion pair, shown here. Similarly, the chlorocomplex of mercury and zinc can be separated using tertiary amine. Thus, ion pair extraction offers high selectivity, efficient separation of ionic species, enhanced extraction of metal complexes, and compatibility with various organic solvents. Further, the third mode or mechanism of solvent extraction is solvation. Here, the solvent itself participates in the extraction of the complex through binding with metal ion, and interest of an alite is called solvation. The basic character of oxygen atom enables the incorporation of solvent molecule in the coordination sphere of the metal ion to form a solvated complex, which can be extracted. An important group of solvent extraction systems is based on the solvation of neutral inorganic molecules or complexes by electron donor containing extractants. Solvation increases the solubility of inorganic species in the organic phase. The oxygenated solvents like ethers, esters, alcohols and ketones and organophosphorus esters solvate the proton and neutral inorganic species, making the extraction of the acids and salts feasible. Example of extraction of solvation is given below in the image. First one is cerium nitrate with ether, second one is vanadium oxide of nitrate with tributylophosphate, and similarly rhenium metal oxide is extracted. The advantage of solvation extraction is its simplicity, high efficiency for neutral complex formation, suitability for various metals, and effective use of easily available organic solvents. Fourth mode of is synergic solvent extraction. Here, synergic solvent extraction occurs when two extractants, used together, produce a greater extraction efficiency or selectivity than either extractant used alone. The two reagents interact to form a mixed ligand complex with the metal ion, which is more easily extracted into the organic phase. The extractant may be chelating agent and solvating agents, or comprise of both two chelating agents and two solvating solvents. In such extraction, chelating agent like 2-the-noyl trifluoroacetone, TTA, and solvating solvent like tributyl phosphate, TBP, and tributyl phosphine oxide, TBPO. Next, here we will see the examples of synergic extraction. First one is uranium-4 ion extraction, combination of HDEHP, D2, ethyl hexyl, phosphoric acid, and TBP, tributyl phosphate, enhances extraction efficiency of uranium compared to either reagent alone. Second one is zinc-2 ion extraction, mixture of LiX63, hydroxyoxime, with TBP gives higher extraction efficiency for zinc-2 ion than either reagent individually. And third one is lanthanide and actinide extraction. HDEHP Jor topo system is widely used for separating rare earth metals and actinides due to strong synergic effects. Last modes of separation, or fifth one is crown ethers or cryptand solvent extraction. Crown ethers or cryptands are macrocyclic compound containing 9 to 60 atoms, including 3 to 20 atoms in the ring. The complexation is considered to result mainly from electrostatic ion dipole attraction between the metal ion situated in the cavity of the ring and oxygen atom surrounding it. These compounds are very good extractants for alkaline and alkali earth metals, and thus, the separation of these metals by solvent extraction became possible. These are multidentate macrocyclic ligands with oxygen, nitrogen or sulfur as donor atoms. Here, we will see the example of this extraction. This image shows the ionic radius of lithium is 0.78 angstrom, sodium is 0.97 angstrom, potassium 1.33 angstrom, rubidium is 1.48 angstrom, and cesium is 1.67 angstrom, and cavity of the elements shows the size range of different crown ethers, such as 12 crown ether shows in the range of 1.20 to 1.50 angstrom, 15 crown ether shows the cavity size of 1.70 to 2.20 angstrom, 18 crown ether shows the 2.60 to 3.20 in 21 crown ethers shows the 3.40 to 4.30 angstrom. Thus, the based ionic radius of elements and cavity size of different crown ethers, it forms the complex and used for extraction of chemical species from sample solution along with extracting solvent. Based on the crown ethers solvent extraction, there will be question, what is host-guest chemistry or supramolecular chemistry? Host-guest chemistry is a branch of supramolecular chemistry where a larger, host, molecule non-covalently binds to a smaller, guest, molecule to form a complex. This interaction is driven by forces like hydrogen bonds, ionic bonds, van der Waals forces, and hydrophobic interactions. Applications include environmental cleanup, molecular recognition, drug delivery, and creating responsive materials. Examples of host-guest chemistry is 12 crown 4, 15 crown 5, and 18 crown 6 are called as a host compound of specific cavity size, and those guest chemical species such as lithium ion, sodium ion, and potassium ion can only accommodate whose size is found in the cavity size, and forming the stable complex. Thank you for watching the videos on analytical chemistry classes, and also topics on solvent extraction, and if you like such videos, please visit these sites for interesting videos for theoretical and experimental lectures. Please click on like it and subscribe it. Thank you.